is visible now, right? You can see it clearly.
Yes, ma'am.
Yes, ma'am. So, ma'am, there is one issue when before starting. Since means this subject is new for this semester, we don't have any previous year question. What get some idea what question can come?
Yes,
Uh,
actually, we will discuss with you some. I will discuss with you some questions regarding my part, and Shashwata sir will do the same thing probably with you. But the thing is, we need to have a class test, right? Uh, I will just talk to Shashwata sir, and then I will inform you. You should find out a suitable date, actually. Probably one of the Saturdays could be good for you to give the class test, because almost all the years class tests are over. So I'm not sure about the modalities. So I will just ask our HOD regarding the modality of conducting class test for open elective, and just will inform you. Okay. Hopefully it will work.
Okay.
If it is in online mode, then there is no problem, you can give it any day. If it is in offline mode, then probably you have to come to, I don't know, I will just check and then I will inform you. Okay, I'm not sure.
Okay, ma'am.
We will inform you about the questions, type of questions, don't worry about it. Okay, in due time. Okay, so I hope it is. Let me just check whether you can see whatever I'm writing, right? It's fine. So, okay. So let us start with the class. And today we are going to move from module 3 to basically module 2, where we will be talking about dynamics of the surfaces, and obviously the interaction forces basically involved for the surface and the potential, and then obviously the chemical and physical interactions, classification of physical forces, and mostly we will be talking about the van der Waals forces, because that have enormous effect or enormous applicability towards colloidal systems. And also we will talk about some other forces which are very very important for colloidal system. Okay, but we will start first with different forces. What is chemical interaction, a very brief overview about chemical and physical interactions, and then classification of physical interactions, and directly then we will go to the van der Waals forces and uh, other forces like the acid base forces, and then electrostatic forces. All those things we will be talking about within due course. And now, uh, so probably I will spend around uh, 5 to 6 hours, 5 to 6 classes rather, on dynamics of the surfaces, only on this part, like the forces, and then what is van der Waals forces, and what we can talk about from the point force sources. With point forces, we can go ahead with the semi-infinite, finite blocks, and how the interactions will play a key role over there. We will talk about all those things. So probably 3 to 4 classes on this, and then later on we will be moving towards wetting and all those phenomena. Okay. Yes. Okay. So basically, uh, when two atoms bind to form a typical non-ionized molecule, the forces that act on them gets involved in the bond formation are referred to as covalent forces, and these are a known phenomena to all of us. And the resulting bonds that actually generated from these forces is known as covalent bonds. Now, in this kind of bond formation, the electrons are basically involved, and they are shared rather by two or more atoms, and the individual character of the atoms are uh, in some extent rather it get lost, okay, because one or more than one electrons are basically shared by two or more atoms or molecules. Now, the formation of metallic bonds also involves this kind of sharing of electrons among a number of atoms, and so that the nature of the bonded atoms actually differs from what is the nature of a free atom that of the same metal that we can think of actually. Now, we know from the general principle of chemistry that uh, the nature basically and obviously the number of covalent bonds formed by a given atom depends on its location in the periodic table. That is quite well known to all of us, and that we can all relate to, and that is also relative to the other atoms that are involved in that particular process, right? And in addition, the covalent bonds have certain characteristic bond lengths, and bond angles which are dependent on the atoms that are involved. That means basically what I mean to say over here is covalent bonds are directional, right? So the number of bonds an atom may form is basically a fundamental property of that atom, and that basically controls how it contributes to the overall structure of the resulting molecule. And the way that the number, the length, the direction of the bonds, uh, that basically controls how the atoms of the resulting molecules can arrange themselves in a three-dimensional patterns or lattices, okay. So that is very very important in terms of whenever we are talking about the chemical bonds. So obviously, we can say that the covalent bonding is of primary importance to the nature of the things that we know them. Uh, However, these bonds, if you see it, they are very very localized. Okay, that means the interaction forces basically um, have a very short range, and they act over a bond distance. If you just see it for the covalent bonds, they basically act at a bond range of somewhere around 1 to 2 nanometers. That has been written over here, okay. So just 1 to 2 nanometer, okay. So that means, sorry, 1.1 to 2.2 nanometer, that is basically 1 to 2 angstrom, okay. So that means you understand that the range of interaction of the covalent bonds, because obviously this is quite understood from the nature of these covalent bonds, because there is a shared electron, only that portion, that interaction forces are or that distance between the bonds, that distance basically plays into the formation of the covalent bond. And most of the covalent bond energies fall in the range of 150 to 900 kilojoule per mole. We'll be talking about it, which is basically around 100 to 300 kt, okay. So this k is nothing but the Boltzmann constant, and this T is the temperature. We will be talking about more of this in later on. Somebody came, just a moment, hold on. Okay. Now, while most of the covalent bonds are strong, they are basically restricted in the range of their actions, and they are in effect limited to the interaction between the atoms involved in molecular formation and formal chemical reaction. So they may be considered as a first approximation strictly of chemical forces. So whenever there are chemical interactions, you find these covalent bonds, and they are basically, we can term it as chemical forces. And that's why the covalent bonds that though they are very very important, they you can find those bonds where the chemical reactions are involved, not in other places. Okay. Uh, so this is basically the chemical interactions that we were thinking of, or we could think of later on. I mean, the other thing is basically the physical interaction. Other than that, there is obviously, other than chemical interactions, there are physical interactions where rather than the intramolecular forces, sometimes we are actually interested with intermolecular forces acting between discrete non-bonded atoms or molecules over the distances which are significantly greater than the distance, than the molecular bond distances that we were talking about in case of covalent bonds. And uh, these bonds are basically, whenever we talk about the physical bond, physical interactions, the bond formation due to physical interactions are generally non-directional. They are non-stoichiometric, and mostly they are basically long range forces. Okay, so that's why I have put over here long range physical forces rather than just physical forces. Mostly, whenever we are talking about the chemical forces, they are limited by the distance, or they are limited their range of action is very, very limited. As I mentioned earlier, it is around 1 to 2 angstrom, while the physical forces are mostly long range. That means the interaction distance between the molecules are quite large, couple of I mean, sometimes it is 100 to 1000 nanometer range. So you can imagine the difference between the chemical interaction or chemical forces or compared to the long range physical forces. So that means the interaction that actually developed due to long range forces are most often, we term it as physical interaction. uh, that basically implies that there is no formal chemical reaction is involved in these particular cases. uh, while the physical interactions do not involve the electronic transformations analogous to covalent bond formation, they can, under some circumstances, be equally strong. So, when we will be talking about the Coulombic forces, we will see that those Coulombic forces are basically of the order of in strength of the order of the covalent bonds, but there are no chemical interactions, or there is no electrons that has been shared between the atoms in that particular cases. But uh, the strength of the forces is of the order of that of the covalent bond. Okay. uh, Physical interactions basically may perturb the chemical electronic configuration of the atoms or the molecules that are involved. The electrons themselves remain associated with their original system. Okay, so this is an important phenomena or difference between the chemical interaction as well as with physical interaction. Uh, while basically all the physical interactions lack the qualifications to be considered classic chemical bonds. It is through such interactions that all but most elemental properties of the materials in our world are determined. They also exhibit themselves as the fundamental factors involved in all colloidal systems. This is very, very important. They are basically also involved in all the biological assemblies and all the natural phenomena that doesn't involve any chemical interactions. That means we are covering a quite a lot of territory where where no chemical interactions are there, but we are talking about the colloids, we are talking about the biological materials, we are talking about the natural phenomena. All of them are associated with long range physical forces. So that's why, rather than just I mean that's why we are focusing on this long range physical forces mostly for colloidal system. We will be talking about the van der Waals forces in general separately, just because it actually holds a wide range of uh, what I say area or application. Okay. Suppose, I mean, I just get one good example actually comes to my mind, so that's why I'm just sharing over here. You see the geckos, right? They can actually climb the wall quite easily. That is basically because of the van der Waals forces of attraction. If you find their fate, you will see that they have I mean lots and lots of kind of a hairy kind of a structure at their legs and also on the bodies, at their foot and also on their bodies, and that basically gives it the strength to hold uh, the wall and then climb to the wall. Okay, so that is a very, 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 very good example of van der Waals forces. That is basically plays a huge role in natural phenomena. Okay, now let us just move towards the uh, classification of physical forces a little bit. We talk about it, and then we will be moving towards the van der Waals forces. So basically, the fundamental physical forces that controls the non-chemical or physical interactions among atoms or molecules are mainly of two types. One is the formal Coulombic or electrostatic interaction that we already know, and then there is another which are lumped together under the general term of van der Waals forces. We will be talking about those in detail later on. But the but the place of Coulombic interactions can be somewhat unclear still in terms of their classification as chemical or physical interaction, because they are of course involved in chemical bonding in ionic molecules. However, they may also be classified as physical interaction because they function over a very wide distance compared to the covalent bonds, and produce dramatic effects on the interactions among ions, ions and polar molecules such as non-polar molecules, and non-polar molecules. If you consider the Coulombic interactions, they are by far the strongest in absolute terms, if we put it, of the physical interactions, and it is equally and or sometimes exceeding the magnitude of the covalent bonds. Uh, However, they are not the most widely encountered type of interactions that we come across, since they are present only in the system containing charged spaces. Also, they are not even always the most important, since many factors can greatly diminish or completely nullify their net effect in a system. uh, Obviously we will be talking about, I mean, we all know about this calculation that I have put over here. So the, if we put the interaction between the two charged atoms or molecules, which is potentially the strongest form of physical interaction to be considered at interfaces and in colloidal system. So the basic concept and equation involves are fundamental to many areas of physics and chemistry, and we are not going to develop those in this particular course. Rather, we will just consider, these are five, sorry. We will rather just talk about it, and then we will shift our focus to the uh, van der Waals forces. So, if we consider 2 point charges, that is Q1 and Q2, the free energy of interaction, which is phi r, can be given by this equation over here, which is Q1 by Q1 Q2 divided by 4 pi epsilon naught epsilon into r, which we can write it in terms of Z1 Z2 into E square divided by 4 pi epsilon naught epsilon into r. Now, this epsilon naught is nothing but the permittivity of a vacuum or free space. Epsilon is the relative permittivity, and r is the distance between the two charges. And obviously, this Z1 and Z2 over here are the valency of each ion, and E is the elementary charge of an electron. Okay, so that's how we get the interaction potential that has been, or energy of interaction that has been given over here. So this is nothing but the potential. Now, the force basically can be obtained by d phi r dr, uh, ddr of phi r basically, and that we can obtain by using uh, this formula over here, q1 q2 divided by 4 pi epsilon naught epsilon r square, and similarly z1 z2 e to the power e square divided by 4 pi epsilon naught into epsilon into r square. And obviously these are, there are a whole lot of other things that is basically there for coulombic forces or coulombic interactions, but as I mentioned earlier, we are not going into the details of that. Rather, we will shift our focus towards the forces. Those are very very important for colloidal systems, because coulombic forces are mostly for the charged particles, not for the non-ionic or non-charged particles. Okay, so that's why we will be mostly talking about the van der Waals forces in this context, and the the different types of forces which are very very important for colloidal system is are basically the van der Waals forces. Van der Waals forces, obviously, it is comprised of three different forces that we will be talking about within a couple of minutes. Then there is Lewis acid-base interactions, then double layer interactions, which is also electrostatic in nature, but they are a bit different from what we have already talked about in terms of the coulombic interactions. And the forces or generated due to absorption or depletion uh, phenomena. Okay, so first we will be talking about the van der Waals forces, and then we will take up one or each one of them separately in later classes. So obviously, all of us know about the Boyle law. So that means it says that the at a certain temperature, pressure and volume are basically inversely proportional to each other. Okay, and it basically doesn't deal with the forces that are acting on the molecules. On the contrary, the van der Waals forces basically are mostly the attractive forces that you can think of. So if you have in a box four atoms or four molecules over there, then the van der Waals forces are mostly attractive towards each other, and that means these molecules will move uh, close to each other. Okay, so the van der Waals forces, which is basically named after Johannes Diederik van der Waals, who has been there from 1837 to 1923, a famous scientist, exist between any combination of molecules or atoms and surfaces. These are not fundamental forces. Why? No. Why not? They are fundamental forces. We'll be talking about it. In fact, they are basically the outcome of electrostatic or electrodynamic interactions, and van der Waals forces are always attractive. These are the the characteristics of van der Waals forces. So even though there is no charges present on a particular surface or particular atom or particular molecule, uh, there also the van der Waals forces will be present. And why so is just answer to that question is this slide over here, where it has been mentioned about the London force or dispersion forces. So let me, before going to these forces, let me just clear it up. The van der Waals forces are mostly comprised of three different forces, that is London forces or dispersion forces. Then there is Debye force, and then there is Kissom force. Okay, so London forces are mainly generated due to induced dipole interaction, whereas Debye force is mostly due to the uh, permanent dipole and induced dipole, and Kissom force is mostly for permanent dipole interaction. Okay, now the what is in whenever I am talking about the induced dipole, that means there is no charges present at the surface at the beginning. Okay, so but obviously, as I from this title itself, you understand that there is kind of a force basically generated due to this induced dipole moment, and that force basically termed as London forces. And this is a very weak force, but this is a very long range force on the contrary, but it will be present in, even though there is no surface charge present on a molecule or atom or a surface. Okay, so due to high frequency, which is a range of, sorry, this is 10 to the power 15 to 10 to the power 16, fluctuations in the electron cloud of a neutral molecule, instantaneously dipole characteristics are developed in the nearby molecule. The coupling of these dipoles in order to minimize their mutual energy results in attractive forces known as van der Waals force, and this force was first explained by London in 1930. Thus, it is also commonly known as London forces or dispersion forces. The London forces or the London interaction free energy at an intermolecular distance x is basically expressed by this equation over here. Phi L is equals to minus Cl into x to the power minus 6, where Cl is the London constant. Okay, so that means in this particular case what happens is, uh, because of the high frequency fluctuations in the electron cloud of a neutral atom, they actually induce the dipole in the nearby atoms. That basically is the reason for generation of this kind of attractive forces. Okay, so this is why London forces are present, even though in none other forces are present in a particular molecule or surface. Okay, so sometimes this is also known as kind of a, uh universal force. Okay, these London forces, because although there is no charge on the molecules, although there is no although those molecules might not be ionized, still there are London forces or dispersion forces present over there. Next is the Debye forces. They are mainly formed due to the permanent dipole induced dipole interactions. So, if a molecule has a permanent dipole moment, it will induce the dipole characteristics in the nearby non-polar molecule, and then an interaction will happen, and that attraction is basically known as Debye forces. And the Debye interactions free energy at an intermolecular distance x is represented by this equation over here, which is nothing but qd equals to minus cd x to the power minus 6, where ct is the Debye constant, and this is obviously the free energy calculation. Okay. Similarly, we do have permanent dipole interaction, which is known as Kisam forces. So when the two molecules have a permanent dipole moment and they experience an attraction, that is basically known as Kisam forces. And Kisam force of interaction or free energy at an intermolecular distance x is basically expressed by this equation over here, which is nothing but phi k is equals to minus ck into x to the power minus 6. uh, how this equations comes, I'm not going into the details of that, because it basically comes from the classical quantum mechanics calculation. So I'm not going into the details of it. Rather, we are just focusing on the final form of the equations. And what we are interested in mostly is this exponent over here. That means they are of the order of minus 6 for all the van der Waals forces. The k over here is a constant considered for a particular type of molecule. So the van der Waals force is a summation of Kisum, Debye, and London dispersion attractive forces, and the potential energy of interaction between the two molecules or atoms due to van der Waals forces is given by this generalized formula over here, which is basically nothing but phi equals to minus beta into x to the power minus 6. So if you look at these three forces, everyone is having an exponent of x to the power minus 6. Phi l equals to minus cl x to the power minus 6. Then we do have for London, we have for Kisum, sorry, for Debye, and we have this for Kisum. Okay, so all of these, if you sum it up, you will obtain this generated equation phi equals to minus beta into x to the power minus 6, where beta is a constant, which involves the constant from each of these interactions. Okay, so basically, whenever we are talking about the van der Waals forces, the equations that we have generated over here, particularly, are due to the interactions between or attraction forces between two point charges, basically separated by a distance x. Okay, so that is basically the potential energy basically given by this equation, and it is the exponent of the distance between the two molecules to the power minus 6. Okay, till now we talked about only the attraction forces, but if two molecules, this is all of us already know this, if two molecules comes very close to each other, uh, they actually repel each other very strongly, and that basically is basically known as bond repulsion. And So when this force, this repulsion force, is added to the attractive van der Waals forces, it gives a potential that is known as Jones potential, and that is basically given by this equation over here: phi prime equals to minus beta x to the power minus 6 plus xi into x to the power minus 12. So if you look at the potential curve, there is basically one attractive forces. So this is basically nothing but xi into x to the power minus 12. হ্যালো, দেবমিতা, আমি একটু ক্লাস নিচ্ছি, আমি পরে ফোন করি তোমাকে একটু। And this is a van der Waals attraction forces, and basically if you just put it over here, so this is basically the van der Waals attraction forces, and if you sum this two up, you will obtain the potential like this, and that basically gives you uh, the Jones potential, what is known as Leonard Jones potential. Okay, and the force you can obtain simply by minus dou phi prime dou x by this derivative, and the minimum, if you look at this equation over here, so therefore basically a minimum distance of equilibrium distance, it can be obtained by simply putting simply actually make a derivative of this equation and putting it to zero, and then you will obtain and equilibrium distance, which is known as basically d naught. We term it as d naught. What is the significance of it? I will talk about it within a couple of moments, but this is d naught, which will be equals to 2 xi divided by beta into 1 to the power 6. Okay. Okay, now before going uh, to the van der Waals forces for surfaces, let us just calculate what will be the d naught for methane, and let us just see how what is the significance of this d naught all about. Okay, so basically for methane, let me just okay, so for methane, basically xi equals to, these data are given, so 6.2 into 10 to the power minus 134 joules meter to the power 12, then beta equals to 2.3 into 10 to the power minus 17, sorry, 17, but 71. So this will be 71 joules n to the power 6. Then if you just put these values over here, you will obtain and d naught equals to 4.2 angstrom, um, and then phi naught is around minus 2.1 into 10 to the power minus 21 joules. Okay, so basically the physical significance of this value of d naught is that uh, the condensed state between condensed state basically the in the condensed state, the distance between the two molecules will be nearly 4 angstrom. Okay, so if you put these two molecules of methane together, if you just put it in a as close as possible, then you cannot go beyond 4 angstrom, you cannot go actually closer to 4 angstrom. You have to have separate two molecules of 4 angstrom, and that uh, will give you a potential of this minus 2.1 into 10 to the minus 21 joules. Okay,
Okay, ma'am.
is it clear?
Yes, ma'am. Yes, ma'am.
Okay. Next, we will try to, till now, whatever we were talking about the point sources or point charges. Okay. So, interaction between two point charges we were talking about, and we just see how that attractions forces can be laid down or can be calculated by using the simple form. Okay. Now I will just take another slide and okay. Anyway, I will explain it over here. So basically, we will be talking about now van der Waals forces between macroscopic bodies. What happens to that? Uh, so till now we were talking about only how the interactions basically varies for two point charges, or rather two atoms or two molecules, and we have talked about the potential as alpha or xi. We can put it in terms of r also, that is the distance between the two molecules, if we are putting it in that way, minus beta to the power, uh, that is r to the power 6. Okay. Then alpha and beta both are greater than 0. So basically the mostly the origin of this van der Waals forces, Liffin's van der Waals forces, is the instantaneous creation of the dipoles due to distortion of electron clouds of neighboring atoms, and the resulting time averaged attractive forces give rise to a negative contribution to the potential, which is captured by this term over here. And while the positive terms basically comes from the um, interaction between positively charged nuclei at a very small distance. And if you just put in a schematic format, I will just put this figure in the next page so that I can have enough space over here. Okay. So basically, we are from this figure, showed you saw that it is basically moving from this to this. Okay, so there is a distribution of the potential over the distance. That is, if I may put it in the r form, I can put it, or you can put it in x terms, that's fine. But now we are trying to simplify that equation in a way, this equation rather, in a way that phi equals to minus beta by r to the power 6 when r is greater than d naught, and phi is equals to infinity when r is less than equals to d naught. That means if I just put it the interaction, sorry, the potential graph, that means we are moving from this towards a situation like this. Okay, that means anything below d naught is infinity, anything above d naught is minus b to b divided by r to the power 6. Fine? Is it clear?
Yes, ma'am. ম্যাম আরেকবার বলবেন এই ফ্যাক্টর?
Yeah, actually what happens, this is the actual equation. Okay, phi equals to alpha divided by r to the power 12 minus beta divided by r to the power 6. That means you will obtain an distributed curve like this, right? Now we are actually trying to simplify it because this becomes a very complicated if we just put it like that way for our calculation. So we are trying to figure it out a way so that phi will be equals to minus b divided by r to the power 6 when r is greater than d naught. Okay, so d naught is the minimum distance or the equilibrium distance that we have talked about previously. In the previous slide itself, we termed
ওকে ম্যাম,
the d naught.
কনডেন্স
D naught is nothing but 2
স্টেটে।
psi divided by beta 1 to the power 6. Yes, sorry.
ম্যাম ওটা মানে এটা নিয়ে বলছেন কনডেন্স স্টেটে 4 2 অ্যাংস্ট্রম হয়ে যাবে।
হ্যাঁ, সেটা মিথেনের জন্য। For a, I have just take a particular example. Okay,
ওকে ম্যাম।
actually, what just try to understand what is the physical significance of d naught. Suppose you are having two molecules, any two molecules. Okay, now you try to put it together in the condensed form. That means you are actually bringing them closer and closer. As soon as you reach to a distance d naught, you can no more bring them together. They will be separated by a distance d naught. Okay, so that is basically the threshold distance that we are, or the equilibrium or minimum distance between two molecules that we are talking about in this particular case.
ওকে ম্যাম, ক্লিয়ার নাও। ইয়েস ম্যাম।
Okay,
ইয়েস ম্যাম,
so
থ্যাংক ইউ।
that's why we are trying to get, or we are trying to put the potential in the form, right? It will be when the distance between two molecules are greater than d naught, then the potential will be only given by minus b divided by r to the power 6. If it is less than d naught, then phi will be infinite. Okay, there is nothing in between. So this is basically our assumption. So
ওকে ম্যাম।
basically, we are doing this only.
Here I'm only taking the attractive force, right?
We are only taking the attractive force. Repulsive force is infinite in cases where r is less than equals to d naught. Fine.
Yes, sir.
Because if we just, because you just see the exponents, we can actually neglect it. It is not a very bad assumption though, but still, if you put it, it will make your life complicated. That's it. Just for the calculation sake, for macroscopic bodies, van der Waals forces between macroscopic body calculation, we are actually going for this assumption for time, for the moment. Okay. So basically, we will try to analyze the van der Waals potential between the two macroscopic particles, which varies with the distance. Now, in order to do that, what is essentially required is, again, I will put this in the next slide because otherwise it will be again very fantastic. So, okay. So, in order to do that, what we need to see, or what we need to think of is uh, because still, because we were able to calculate the interaction between 2 point charges or 2 point or two atoms. Okay, so if we can think that each particle is basically made up of a large number of molecules of only one kind, and the total energy of the system basically comprising two particles is the sum of the respective arising due to molecular interaction, and the third one, common molecule in one particle interacting with the other, then compute it. Okay, so that is what we are trying to do is, let me just put it in a simple form, is that we are simply seeing that there is one molecule or one atom in one of these macroscopic body, and in the other macroscopic body we are trying to take a circular element. Okay, and we are seeing that what will be the interaction of this point charge with the uh, uh, of this atom with the atom present in the actually integrated for the whole circular element, and then we will try to integrate it for the whole slab. Let me just go through the calculations, then probably you will understand it more clearly. And and also in this particular case, basically mostly we are interested in finding out the forces between the particles. And since the forces are force is negative gradient of energy, so while calculating the Lipid van der Waals energy potential for a two particle system, we only considered the cross interactions. Okay, because they vary with interparticle distance. And we will try to see how we can actually use this cross interaction, cross particle interaction for our calculation, to incorporate it in the calculation of the self energy. We will try later on, but for timing let us consider only the cross interaction between the molecules and try to get a value of it. Okay, so uh, let me just, okay, no, no, this one. Okay, so basically consider two flat parallel slabs with slab-like particles, which is having a distance of, say, this is, because this is slab 2, so this is D2, and this is slab 1, so the distance is D. Okay, and van der Waals interactions are short range and are generally effective with a distance of d is nearly 10 to 100 nanometer. Okay, uh, and this is the particle coordinate system for us that we have to actually remember. So this is z, this is y, and this is our x direction. Okay, so, in order to calculate the total Lipschitz van der Waals interaction potential, first a molecule from the slab 2 is basically taken, and the interaction energies with all the atoms present in slab 1 will be summed up, and and we will actually assume that the surrounding molecules doesn't affect the interaction potential between the two molecules under consideration. So that is our assumption. Presence of around molecules does not affect the interaction. Potential between the two molecules under consideration. Okay, so this is our assumption, and so let me just take another slide. Okay, so as the Diffie van der Waals potential is a function of the distance r between the molecules, one must choose the integrating volume in a slab, uh, which is the locus of all the equidistant point from the chosen point in slab 2, and that basically is clearly this thin molecule that we are thinking about. So this is not very clear, but if you just put it in it goes something like this. Okay, so this kind of a circular ring that we were thinking of, and this is just the front face of that if you are putting it. Okay, so if you just put when dv represents volume elements, then dv over here is nothing but 2 into pi into y dy dk. Okay, so we have here this is just a thickness of circular ring, and this is basically this distance over here, that is L dy. Okay, so we can write volume of that element will be dv equals to 2 pi dy dk. And also we try to define rho 2 m1 are the viscosities, and these are the molecular weights. Of nuclear bond, and so we can write this the number of molecules per unit volume in slab given by basically molecules or atoms molecule divided by volume, which will be equals to rho 1 into A divided by M1. This will be nothing but gram per centimeter cube atoms per mole, and then per gram. Okay, without
Yes, ma'am.
জিজ্ঞেস করবে। Now, so here actually simplified already our equations for interaction or the van der Waals potential. So using that simplified form of Life's van der Waals potential between the two molecules, which is what we say that phi equals beta divided by r to the power 6 for distances between d naught, that we'll be using over here, and by using that using that equation basically, if we just multiply with the number of molecules present in the integrative volume, you can get the interaction potential between a single molecule into with the annular element slab 1. Okay, so that's actually basically the we can obtain d double prime is the d phi double prime is basically the interaction potential between a single molecule or atom present in slab 2 with the annular element or the circular element present in slab 1 can be written in terms of minus rho 1 into Na divided by M1 into dV beta to the power 12 divided by, sorry, beta to the beta 1, that is interaction between slab 1 and slab 2, r to the power 6. Okay, so this, if we integrate it, you will obtain phi double prime will be equals to, sorry, d phi double prime. I mean, we are just simplifying it. We are putting this dv over here. So minus rho 1 into Na divided by M1. This will be equals to 2 pi y dy dk beta 1 2 divided by r6. And from uh, Pythagorean, you can write it. We can write that r square equals to y square plus z plus k whole square. So using this into the previous equation, if we put it, we will obtain you can put that value over here, and obviously we will obtain 2 pi y into dy dk into b12 divided by this rather than r to the power 6, if we put r square value over here, y square plus z plus k whole square whole to the power cube, I will obtain in this equation. Okay, now if you just try to actually integrate it between the appropriate limits with for the phi double prime, then you can get it from for k, you can obtain it, you can actually integrate it from 0 to d1, and for y it will be 0 to infinity. You will get the net interaction potential, net interaction potential by double prime between the selected molecule in slab 2 with the entire slab 1. Phi double prime will be given as equals to d phi double prime, which will be equals to minus 2 rho 1 in A into phi m1 k equals to 0 to 2 y equals to 0 to infinity. আমি এই পুরো টার্মটা এখানটায় লিখছি, হ্যাঁ, this is will be equals to y divided by y square plus z plus k square whole cube into dy dk, right? So you will obtain it. This you can write it further. This that will be basically equal to 2 into rho 1 na pi beta 1 2 divided by, okay, there is a minus, I don't know, yeah, I put it over here, I forgot to put it. This will be equals to m1 k equals to 0 to d2 1 divided by 4 z plus k whole to the power 4 dk, and this will be further simplified to 2 to 1 in a y beta 1 2 divided by n1. This can be written in terms of 1 by 12. Uh, 1 divided by z cube minus 1 divided by z plus d1 whole to the power cube. This one, which can be written in terms of rho 1 minus na pi beta 1 2 divided by 6 in 1, um, 1 divided by z cube minus 1 divided by z plus d1 cube. Okay, so now this is the potential interaction potential between the one molecule in slab 2 with the entire slab 1. Now we want to actually
Ma'am,
consider the whole. Yes.
we integrate k equal to 0 to d2 and we writing here z plus d1.
Yes.
Ma'am, it should be d2. K 0 to d2.
No, sorry, this will be d1. Sorry,
Okay, ma'am.
let me just once again check it. D1 it will be. Sorry. Extremely sorry. This will be for D1. Here I have written D1. Okay, here I have written D1. Sorry. This will be D1. I don't know whether I have written somewhere else. If I have some, okay, I have written. This will be D1. Okay. So this is for the for molecule one molecule in slab two and the entire slab one. Okay, that we have talked about. Now we will be talking about or we will try to get in, involved of entire slab 2. In order to do that, what first we will do is we will try to locate an element which is where that molecule is actually based, and then we will try to integrate the whole of this slab 2 over here. Okay. uh, So we are thinking that this molecule that we have first assumed, which is basically situated somewhere between this dz, this element, within this element. Okay, so we can now the if we are just that dg initial interaction within this thin integrating volume, and the entire slab 1, then we can write it as equal to pi divided in rho 2 into Na divided by m2 into dz. Okay. So equals to d, and this is z equals to d plus d2, and that equals to d to z equals to d plus d2 in order to get the whole slab in this range. Okay, and then you can obtain the final expression between the potential interaction between entire slab 2 with that entire slab 1, right? Isn't it?
Yes, ma'am. Yes, ma'am.
Yes,
Okay,
ma'am.
so we can write as g will be equals to integration of dg. Let me just put it. So this one will be starting from z equals to d to z equals to d plus d2, and then we do have this phi double prime rho 2 into na divided by m2 into dz. Okay, so that actually basically if you put that phi double prime, so this will give you d to d plus d2. I don't know what happened to today's pen, I couldn't write it. So okay, so this will be equals to rho 1 into rho 2 into na square. I'm just putting the value of phi double prime over here. Okay, then pi beta 1, sorry, beta 1 2 divided by 6 m1 m2 into 1 by z cube minus 1 divided by z plus d1 cube into dz. Okay, so if you simplify it, you will obtain this equation. G will be equals to minus A. A is the Hammer constant. I will just let you know. Let me just write the final form, and then 1 divided by D plus D1 plus D2 square plus 1 by D square. If you just simply do the maths, you will obtain this. You just need to integrate it. That's it. Minus 1 divided by D plus D1 square minus 1 divided by D plus D2 square. Okay, and this A12 is is known as Hammer constant, and that is nothing but rho 1 into rho 2 pi square into n square into beta 1 2 divided by n1 n2. And it does have a unit of energy, that is basically args, or in terms of, if you are putting in SI, it's joules. For two bodies in vacuum, placed in vacuum, the value of this constant basically varies between 10 to the power minus 19 to 10 to the power minus 21 joules, or you can put it in terms of zero point 0.1 to around 10 kt. In that range, it basically varies when you are putting two molecules in vacuum. Okay, so basically, what you have to note over here is that this Lipid van der Waals energy of interaction is per unit area, and in reality, if there were two slabs of areas A1 and A2, such that A1 is less than A2, suppose there is areas A1 is less than A2, one will multiply G with A1 to get the total Lipid van der Waals energy of interaction. You can ignore the end effects, and assuming that the Lipid van der Waals forces decay faster enough in order to be able to ignore the contribution from A2 minus A1, that difference. Okay, and the most important thing from this discussion that we have done till now is that the rate of decay of Lipid van der Waals forces, Lipid van der Waals potential between two molecules or atoms goes with r to the power minus 6, if you remember it properly. Then while the decay is with z to the power minus 3 for the interaction between a single molecule and a macroscopic body, and d to the power minus 2 in case they are between two macroscopic bodies, right? This is the main takeaway from all this discussion. That's why these are basically known as long range van der Waals forces. And if you just put your d1 and d2 is greater than 100 nanometer, then basically what happens is your expression basically reduces to g sorry, g equals to minus a12 divided by 12 pi d square. This is nothing but two infinite slab placed in vacuum. And forces between such bodies will be given as minus dg by d which will be equals to minus A12 divided by 12 pi dq. Sorry, it's 6, 6 pi dq. Okay.
Okay.
And when you just make these two infinite bodies, they come closer to each other, the value of g become more and more negative. And however, at a very small distance, the repulsive forces should be take over, and the uh, uh, contact between two bodies will be defined at a distance of d equals to d naught, as we have mentioned previously, and that basically given by g d naught equals to minus a12 divided by 12 pi d naught square. And they cannot come closer anymore other than this d naught. And also, let me just take another 2 minutes and I will just complete it. So basically, whatever we have derived till now uh, is for macroscopic observables. And if you can recall, I don't know whether you have came across this Griffith van der Waals energy of adhesion, which we can define it. I'm sure Shashwat sir has already mentioned it before. So this will be, you can write it in terms of g d naught minus g infinity, and then that you can put it, it will be equals to minus a12 divided by 12 pi d naught square, which will be equals to nothing but your gamma 1 2 Griffith van der Waals interaction minus gamma 1 Griffith van der Waals interaction, and minus gamma 2 of Griffith van der Waals interaction. So basically, okay, and if we try to put it in place of one, okay, so basically we can write it. I will just take another slide over here, it will be easier for me to write. So so basically what we can write it from that equation is a12 will be equals to minus 12 pi d naught square gamma 1 2 lw minus gamma 1 lw minus gamma 2 lw lw. So basically, from this equation you can see that the Hamaka constant, which is A12, is a molecular parameter, and they can directly be correlated towards the surface tension values, which you can measure from the experimental point of view, or experiment, by using simple contact angle measurements. And by simply putting in place of 2, if we want to put a11, if we try to get the interaction of a11, then we can obtain it by simply by this 2 to 4 pi d naught square gamma 1 lw, and a22 will be 24 pi d naught square gamma 2 lw, because gamma 11 lw equal be gamma 22 lw will be equals to 0. And if the field equals to square root of beta 11 beta 22, okay, and then we can obtain a12 will be equals to square root of a11 a12, that we can write it in terms of 24 pi d naught square root of gamma 1 lw gamma 2 lw and gamma 1 to lw will be equals to square root of gamma 1 LW minus square root of gamma 2 LW whole square. Okay, so this is where this the van der Waals forces between two macroscopic body can directly be related to the interfacial forces, or the which you can actually calculate from normal contact angle measurements. Probably this part তোমরা কি contact angle পড়ানো হয়েছে একটু? Did you get an idea about the contact angle? No. Yes. সবাই বাড়ি চলে গেছে নাকি?
হ্যাঁ ম্যাম আছি অ্যাকচুয়ালি। লাস্ট ক্লাসটা ম্যাম অ্যাকচুয়ালি শাশ্বত স্যার
সারফ্যাক্ট্যান্ট শুরু হয়েছিল
করতে
লাস্ট
পারেন।
ক্লাসে।
হ্যাঁ স্যার,
So, ম্যাম কন্ট্যাক্ট অ্যাঙ্গেলটা করাইনি এখনো অব্দি, বাট প্রিলিমিনারি নলেজ আছে।
হ্যাঁ, প্রিলিমিনারি নলেজ আছে তো। সো প্রিলিমিনারি নলেজ থেকে just try to see the correlation between these two, but later on probably আমি জাস্ট মডিউল 2 তে probably কন্ট্যাক্ট অ্যাঙ্গেল আছে কিনা দেখতে হবে। তখন যখন পড়াবো তখন আবার এই জিনিসটাকে আরেকবার নিয়ে আসবো, ঠিক আছে?
ওকে ম্যাম,
ওকে
ওকে
ম্যাম।
ম্যাম।
So it is here of what we are trying to do in this particular class. We were actually trying to get
ম্যাম
information
লাস্ট
from the
স্লাইডটা
point
আরেকবার করিয়ে
sources.
দেবেন।
Last slide টা
লাস্ট স্লাইডটা তাহলে নেক্সট টাইম একবার করিয়ে দেবেন আরেকবার।
হ্যাঁ, লাস্ট স্লাইডটা আরেকবার আমি রিক্যাপিচুলেট করাবো when we were talking about the contact angle. ওকে,
ওকে
তখন এখানে ওই এই ইকুয়েশনস গুলো আবার লিখবই, আমি লিখতেই হবে আমাকে, ঠিক আছে?
ওকে ম্যাম, ওকে ম্যাম।
ওকে ম্যাম।
But what we were trying to do is we take the point charges, we try to get the equations for the point charges, then we try to get a hold of what we can do, or how we can actually correlate that, or we can apply that for the materials of blocks for bodies, and we have successfully, right? We have started taking one molecule and one circular ring in which is basically all the molecules equidistance from this molecule in slab 1. We tried to write down the equations, then we integrated it for the whole slab 1, and then we take an element in the slab 2 where this molecule is situated, and then we integrated the whole slab. That was the main idea. Fine. In the next
Yes,
class,
ma'am.
we will try
Yes,
to
yes,
see
ma'am.
some application of this.
ওকে ম্যাম, ওকে ম্যাম।
Okay, thank you so much, all of you. Next class, please come within 4:30 so that we can start it early. Okay?
Yes ma'am, surely. Sir,
Okay,
actually,
ma'am.
ma'am, actually
Okay.
today we had a confusion regarding the link of the class. So now we know that it will be based on the previous link's
Yeah,
class
actually,
only.
I mentioned in the last class also, so that's why I didn't actually inform you.
Okay, ma'am.
Okay.
No, ma'am. It's our
Please
actually. Ma'am.
remember it that
Recording.
I'm
Okay,
not
ma'am.
going to inform, because it's very difficult for me just to remember, in the previous day that I have to inform you, and for the class and all. But I will be there. In case I cannot attend the class, I will inform you. That is more clear.
Okay, ma'am. Okay. Thank you.
Okay, ma'am.
Okay.
And ma'am, regarding the mode of the class test, ma'am, most of the other class tests that has happened till now for the other subjects,
Yeah.
those have been in online mode so far. So, like
Yeah,
the
I
offline,
will just yes, I mean, I have no problem. I mean, if it is in online mode, I have to just get an information from our HOD. What is there? Is there any rules or not? Okay?
okay, ma'am. Okay,
I
Okay,
will
ma'am.
let you know. In due time.
okay. Thank
Okay.
you, ma'am.
Thank you so
Thank
much.
you,
And
ma'am.
all of you have got the previous notes, right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. Thank you.
Thank you, ma'am.